Exploring the Solar System Part 2, how we explore the solar system with spacecraft. So I'll be asking the question, how do we get there? And what do we do then? Having sent a spacecraft to another planet, what do we do when we get there? And although in principle we send spacecraft to planets to get some information, we may want to record lots of different things. We might want to record the characteristics, the properties of what's going on the surface, but most people are interested in, can we get images of whatever the spacecraft see? To hell with the fact that we might want to measure the magnetic field and the temperature and the pressure and the composition. Basically, most people are interested in, let's see the images. So how do we get images back from these spacecraft? And again, at the end, I'll be asking the question, what next? What lies in the immediate future for spacecraft exploring the solar system? I wanted to start by just recapping the fact that we have actually sent a lot of spacecraft into the solar system. And I wasn't sure how many before I wrote this talk, so I thought, well, how many spacecraft have we sent out into the solar system? And I soon ran out of fingers when I realized there's an awful lot, so I tried to list them. I know you can't read this list. That's up to and including Europa Clipper, which was sent a few months ago. So over the last 70 years, basically the space age, or another way of saying it, all of my life, because I was just about born into the space age, we have sent an awful lot of spacecraft out there. Some of them fairly local to the moon, but many of them to the outer reaches of the solar system. So there are an awful lot of, if you like, robots exploring the solar system. For getting to Mars, as I intimated last time, it's not that difficult because Mars is only the next planet out from Earth in the solar system. So if we think of the Earth going around the sun and then think about the next planet out, Mars going around the sun, none of this to scale, this is just a cartoon. If we want to get from the Earth to Mars, we can do that by leaving the Earth and firing a rocket that puts us on that blue line, that blue trajectory. There's a particular transfer which is the most efficient way of getting from Earth to Mars. If I take the orbits away, you see it's actually an orbit around the sun. It's an elliptical orbit around the sun. We have to give it a kick when it leaves Earth, and then we can arrive at Mars. It looks like if you miss Mars, you come back to Earth again. Well, it's not quite as simple as that, because if you were to go on that blue orbit, it takes about 1.5 years to complete that orbit. But how long does it take Earth to go around the sun? About 1 year. So if it takes you 1.5 years to come back, well, Earth isn't there anymore because Earth has now traveled halfway around the sun. So that's why getting to Mars and back is such an issue. You have to be very careful as to how you plan the timing when you leave and when you're likely to come back again. But in principle, not that difficult because Mars is quite close. So you don't need a huge rocket if all you want to do is to send a few tons of rover, for instance, to Mars. But back in the 1960s, it was realized, well, hang on a minute, if we want to travel to other parts of the solar system, what if we want to explore Jupiter, Saturn, Uranus, and Neptune? It was realized that you can use a so-called slingshot, a gravity assist, as it's properly called, but most people would call it a slingshot, to send stuff from the Earth, and as it passes Jupiter, let me just run that animation one more time. Once we leave Earth, the spacecraft can go past Jupiter, and Jupiter gives it an extra kick. Boom. It sends it off in a different direction and a lot faster, which means you can save fuel and you get a boost sending you on to the next planet in the solar system, if you time it right. And it was realized in the 1960s that there was an opportunity which led to the Voyager programs, Voyager 1 and Voyager 2, that if you get the timing right, you can send a probe to Jupiter, which will slingshot you onto Saturn, allowing you to explore the solar system faster and cheaper. Less fuel means you have more mass to play with for your scientific instruments. You can take better cameras or more instruments with you. And then Voyager 2 did the same thing, launched from Earth, a gravity assist from Jupiter, which flung it on towards Saturn, and they got the timing right so that Saturn gave you an assist, a gravity assist, and flung you on towards Uranus, which again gave you a gravity assist and flung you on towards Neptune. So even though you're just using one bit of fuel to get you off the Earth, the planets give you the extra boost to allow you to explore Jupiter and Saturn and Uranus and Neptune all in one go, which is why the Voyager program was so successful. They built the spacecraft extremely well so that even though it was traveling for decades rather than years, it managed to explore the outer solar system a lot faster than it would if it had to simply fire rocket engines to get it all the way out, for instance, to Neptune. So a nice idea. One of the very earliest images, this wasn't taken by Voyager. Does anybody know which particular body this is? This is the far side of the moon taken with Luna 3. This is going back to 1950s technology. We can tidy it up a little bit with modern noise reduction algorithms. This image was taken in 1959, and it looks a little better when you take some of the noise out, but it still looks a little bit fuzzy and a little bit low resolution. But this is 1959. I was sort of 1 year old when this was actually taken. And the technology required to get this image, again, we take it for granted that we all carry around digital cameras with us in our phones and elsewhere. But back in 1959, there was no such thing. So how was this image actually acquired? Well, amazingly enough, this image was taken on film. Yes, film. You remember that? The film was exposed. Then the film was developed in a chemical bath, and then it was fixed, and then it was dried, and then it was scanned, all on board the spacecraft. It didn't come back to Earth to be developed. It was developed on the spacecraft. Then it was scanned by a cathode ray tube spot scanning over the film onto a multiplier, and then the signal from the photomultiplier was transmitted back to Earth, which then reconstructed the image, like a fax machine, for those that can remember fax machines. Just for comparison, that's what the far side of the moon looks like with the most recent technology we have, the Lunar Reconnaissance Orbiter. Notice that everything is in the right place. So even though it's 1950s technology, it did give us a good indication of what the far side of the moon looked like, because up to that point, we had no idea, because the moon always has one face facing the Earth. We see the near side only, and that has a whole load of seas and craters and mountains, but the far side, we weren't sure what it looked like until these first imaging technologies were available. But it wasn't long before people said, taking film and then scanning it and then sending the image back to Earth, that is a painful way of doing any imaging. We've got to do better than that. So it was only a few years later that we had the world's first digital camera. If you're grateful for having a digital camera in your phone, bear in mind the world's first digital camera was not built for use on Earth. It was built for a probe going past Mars. The world's first digital camera was this one sitting on the underside of Mariner 4 and Mariner 5 spacecraft. As they flew past Mars, the images from this digital camera were stored onto tape, and then after the flyby, which usually is quite fast, same with Voyager, it doesn't stay there, it just flies past the planet and then moves on. So it was only a few hours of imaging stored on tape, and then after it had flown past the planet, the tape is rewound, and hopefully the information is then sent back to Earth so that you can reconstruct the image. So this was in the mid-1960s. They really did hope that the tape not only started to run when the images were being taken, but also they hoped it would stop. Otherwise, it would continue recording images from the camera, and once it had gone past Mars, it would just be recording nothing. It would just be recording empty space. Luckily, it all worked, and the tape machine did replay correctly, and we got the first digital images of another planet in the mid-1960s. Again, with a little bit of image reduction, it cleans up quite nicely. And again, you can see detail in there. Not the same resolution as we're now used to with modern technology, but for the 1960s, this was absolutely wonderful. So we've now visited all of the major bodies in the solar system and a few of the smaller ones as well. We've visited asteroids as well as the planets, all of the planets from Mercury, and dwarf planets such as Ceres and Pluto and other bodies beyond Pluto in the solar system. I'm not going to have time to talk about all of them, so I've just picked a couple of examples of the sort of spacecraft that have been exploring the solar system in past years. Cassini is a spacecraft that was sent to Saturn, and it was looking at Saturn from about 2004 until it was finally crashed into Saturn in 2017. Why did they bother crashing it? Why didn't they just let it power down and just keep orbiting the planet? Well, there's the outside possibility that although the planet cannot harbor life as far as we know, there is the possibility that some of its moons might. Same as Jupiter. Some of Jupiter's moons might harbor life. Jupiter, no. Saturn, no. But moons, maybe. So they didn't want the Cassini spacecraft one day to accidentally crash into a moon and contaminate it. So they decided to crash it into Saturn to make it, as it were, safe. It was orbiting Saturn for years and years and years, imaging Saturn, imaging the ring system, and imaging the moons to try and understand what the moons are doing, how they affect the ring system, and the makeup of Saturn itself. A few numbers there, which I'm not going to go through, but just a reminder that it's traveled billions of miles in its trip to Saturn and its orbit of Saturn itself. And huge numbers of images taken, something in the case of Cassini, perhaps 500,000 images were taken of Saturn and its ring system and its moons. Huge amounts of data because, of course, with digital technology, it's now possible to do that and transmit the signals back to Earth by radio. Would have been very impractical to take film and develop it and fix it and scan it and do the same. So it's just as well digital technology came along. Just for scale, in case you're struggling, there's a human standing next to the Cassini spacecraft. So it's huge. It's taller than this particular ceiling in the room we're in. And if we compare that with a Hubble Space Telescope image, that's the best that we could possibly see of Saturn as seen from Earth, from the Hubble Space Telescope. So it has a lot of detail of the surface, and of course we can see some detail in the rings. But if we were to look in more detail and ask, well, okay, we can see something there, but what would we see from Cassini, which is of course much closer to the planet? Then we see an enormous amount of detail in the rings. We realize the rings are not by any means a solid disk. They are trillions of small particles, each of which are orbiting the planet separately and are being shepherded into particular structures where there are some bright areas and some dark areas and some gaps and some weird structures, as well as moons that seem to be shepherding some of the particles in the ring system into place. When you look at it from certain angles, it looks like a long-playing record, for those of you who remember long-playing records. We have to remind ourselves that the ring system is huge in terms of diameter, 250,000 kilometers in diameter, but perhaps only a few meters thick, certainly less than a kilometer thick, but hundreds of thousands of kilometers in diameter, the thinnest, flattest thing in the solar system. And at certain times of the year, the sun comes across the rings rather than down onto the rings. It comes across the ring plane, and we see the sun casting shadows of something that looks like, based on the shadows that we can see there appear to be bumps. Most of it appears to be very flat, but every once in a while, some of these bits of the ring system appear to be very bumpy. Some of these lumps can be a few kilometers in size, much larger than the bumps in the rings. Trying to understand why they are there and what the shepherd moons are doing in terms of tugging on all of these particles in the ring system, that's part of what Cassini and similar spacecrafts are doing, trying to understand the dynamics of how this system works, how it came to be. Will the rings always be there, or are the rings changing slowly with time? One thing you can do with a spacecraft that you can't do by looking from Earth is you can fly into the shadow, and basically what we're looking at here is Saturn seen with the sun illuminating behind it. You can't do that from Earth. The sun is always behind you, and you're looking at them effectively fully illuminated. But with a spacecraft, you can go behind Saturn into its shadow, look backwards, and you see the sun shining from behind. So the sun is shining through the almost transparent-looking rings here, and that is giving you more information about how light is scattered by these particles. It tells you something about the size of the particles that you're looking at, and also gives you a rather beautiful image as well. A spacecraft that was along for the ride, that's Cassini, but sitting on the side is a small extra spacecraft called Huygens, and that was a stowaway, if you like, the idea being Cassini would study Saturn, but Huygens would be dropped into the surface of Titan. Titan, remember, one day we may send a helicopter there, but the idea was drop Huygens into the atmosphere of Titan And as it went down, it took this particular video. So we know that Titan has got a very thick atmosphere, but because it's got a thick atmosphere, we're not too sure what the surface looked like. So the idea is drop a probe into the atmosphere. As it came down through the rather hazy orange atmosphere, it started to show us what the surface of Titan actually looks like. And what we ended up seeing for the first time was mountains and valleys and river channels and lakes and clouds and rain. So no, it's not the same as the Earth. A lot of this is probably not water. It's probably other elements and compounds, but it seems to have a lot of the features of planet Earth. So it's a very interesting world in its own right, even though it's only the moon of a giant planet. It's a reminder that moons are not boring. Moons can be really interesting in their own right. Another example of a probe relatively recently, this is Juno, which is still going around Jupiter as of 2016, so it's a little less than 10 years old now. It took a 5-year journey to get there, but then it's spent a decade or so looking at Juno. Again, I won't go through all the numbers, but terabytes, thousands of gigabytes of data have been taken on lots and lots of images and then transmitted back to Earth. Jupiter is interesting for a number of different reasons. It has these characteristic cloud belts, which you can see even in an amateur telescope. A small telescope will show you those cloud belts. If we unwrap it so we can see it a little more clearly, it's clear that these cloud belts, some of them are quite bright, some of them are quite dark, some of them look a little bit reddish, some look a little bit whitish. Trying to understand why are they different colors. There's also storm systems there, which appear to be churning up material from different heights. It is thought that perhaps the white areas are ammonia ice. It's thought that the dark reddish areas might be other elements coming up from below, maybe sulfur, maybe phosphorus. One of the reasons for sending these probes to other planets is to find out what they're actually made of and again, how they work. So the Juno spacecraft is in very big orbits around Jupiter, and every once in a while it swoops close to the surface of Jupiter and takes images like this. The amount of detail that can be seen from these spacecraft is absolutely phenomenal. Notice the occasional white flash. That's lightning in the storms of Jupiter. The colors have been exaggerated so we can see them a little more clearly. It's not quite that amount of blue, but they've been enhanced to make it easier to see. And as it swept close to the planet, this is a time lapse. It actually took a few hours to pass the planet itself. As it came out the other side, again, we see the polar regions looking a lot bluer than the equatorial regions. We see these white spots. What are they? Storm systems. Why do these storm systems seem to last so long? The great red spot on Jupiter appears to be a storm system which has lasted for at least 400 years. Why don't storm systems dissipate? On Earth, they dissipate and other new storm systems start. On Jupiter, some storm systems seem to have been around for an awfully long time. Understanding that might help us understand our own climate. There's just a static image which again shows you the phenomenal amount of detail that the digital cameras on spacecraft can achieve if you get everything right. If you get the exposure right, if you point in the right direction, you have to make sure your camera is looking in the right direction at any given instant to make sure you're looking at what you want to look at. But of course, NASA and ESA and other space agencies are now expert at getting spacecraft to do what they want to do. In this particular case, this is a part of Jupiter. It really does look like a watercolor that's just been left out in the rain and starting to smudge. People have debated as to what this black spot in the middle is. It's thought that maybe this is a vortex and we're actually looking down into the actual atmosphere of Jupiter, but there's still debate as to exactly what's going on and why the colors exist in terms of what elements are being dredged up or stirred up by these storm systems. In this case, Juno was only some 15,000 kilometers or so above the surface. When you remember that Jupiter is 10 times the size of Earth, this really is skimming over the cloud tops. If we have a look at a little animation, we can see just how complex the cloud systems are on Jupiter. This is only a few seconds, but it reminds us that there's an awful lot going on. Even if we just look at a small bit of Jupiter and watch it for a few minutes or a few hours, there's so much going on there, it'll keep students, astrophysics students, going for years trying to understand how the storm systems work. But of course, the solar system itself is not just the sun and 8 planets, despite this orrery implying that that's sort of all there is out there, plus a few other bits and pieces. New Horizons, for instance, was sent out to have a look at Pluto, a dwarf planet, and its moon Charon, and it's simply gone past and has kept going. So it's now exploring what's outside the solar system beyond Pluto, the so-called Kuiper belt, full of interesting objects, if only New Horizons can figure out where they are. There's a limited amount of fuel on board. It can't simply go where it wants to go. It's flying and escaping the solar system, and they are trying to figure out, is there anything interesting on its path that it could possibly photograph on its way out of the solar system. In addition to planets and dwarf planets, there are some 300 moons. We have got one, Mars has got 2, Venus has got none. Saturn and Jupiter between them have got hundreds of moons. So there are huge numbers. Here's just a very small selection. There's our familiar moon in the bottom right. Some of them look more like the Death Star from Star Wars than a moon. Some of them look vaguely circular. Some of them look more like potato-shaped. It depends on their size. Generally, large ones tend to be almost spherical. Smaller ones tend to be a bit more irregular. But some of the larger moons in the solar system, here they are to scale rather than just a pastiche of them. Here's Titan, the rather fuzzy-looking moon, because it's got such a thick atmosphere, we can't really see any surface detail. You can see it's actually much larger than our own moon. And the moons of Jupiter at the top here are also rather interesting. The one on the left, looking more like a pizza than a moon, is Io. That seems to be rather volcanic and still active, unlike the volcanoes on Mars. The volcanoes on Io appear to be really active because there appears to be a heat source which is continually recirculating material, and the yellow color is presumably a lot of sulfur that's in the system. But it's not so much Io that's interesting for most people, it's the other 3 moons of Jupiter, the so-called Galilean moons, because Galileo first saw them. Europa, Ganymede, and Callisto, the so-called ice moons. They appear to be completely covered in ice. And if you say, well, if they're just ice, well, it's just going to be like Antarctica, isn't it? It's going to be really boring. There's nothing happening. But it would appear that they are ice moons with water underneath the ice. It is thought, there are reasons to believe, that the total amount of water on those moons is more than the water in, well, all of Earth. The entire Pacific and Atlantic Oceans don't add up to all of the water on these small moons of Jupiter. So it would appear there are worlds out there, despite being a long way from the sun, in which water exists not only in the form of ice, but in the form of liquid water. Whenever you have the right elements, and you have liquid water, and you have a heat source, whatever that heat source may be, then you have the 3 ingredients for life to start. So the question is, have these things existed long enough for life to start in the oceans which are underneath the ice of the Jupiter ice moons? Of course we don't know, and we want to find out, which is why ESA have launched the mission JUICE as of 2023. That was launched, Jupiter's Icy Moons, otherwise known as JUICE. And NASA have launched as of October last year the Europa Clipper, because they want in particular to have a look at Europa. That is thought to be the most likely to have life in its under ice oceans. So 2 missions on their way. It'll take a little while for them to get there. Jupiter's still a long way away. So it'll take them a while to get there, but JUICE and Europa will be exploring the ice moons of Jupiter in the next few years. I said earlier that when we do explore these planets, we get all the images and all the other data back by sending radio waves back to Earth. But in the future, we may be doing it differently. And a test has been done by sending a craft to one of the asteroids called Psyche. So up till now, it's always been done by a radio transmitter on the spacecraft, beaming the data back to an even bigger radio dish on the Earth. It needs to be huge because of the distance involved. And the radio signals will then be decoded and converted back into data and or images. But radio is not necessarily the most efficient way of getting data from A to B. And this latest mission to the asteroid called Psyche did a test. And the test was, what if we don't use radio waves? Why don't we use a laser? Some of you have broadband in which a fiber optic cable is bringing the information in and out of your house. Information can be sent down a laser at much higher data rates than it's possible with radio. So why don't we have a laser on the spacecraft beaming its data back to Earth, and instead of picking it up in a huge radio dish, we pick it up in an optical telescope. That is the Hale telescope. That was the biggest telescope in the world when I was born. It's since been overtaken by larger telescopes, but the bottom line is, why can't we use optical telescopes to pick up the flash from a laser and decode any signals on it? So this test was carried out. They didn't say to themselves, let's just send a picture of the asteroid we're aiming for. That would just be one image. They wanted a real test of how fast they could get data down a laser beam. So they wanted not an image, they wanted a video. Lots and lots of data in a video if the video lasts a few minutes. So if you're going to send a video down a laser beam, what video do you choose? Somebody at NASA thought, wouldn't it be fun to choose, for the first experiment, a cat chasing a laser? So this is the test video they sent from a spacecraft. And it's one of the NASA employees' cat chasing a laser. And they managed to prove that even though the spacecraft was 50 million kilometers away, they got data rates of 260 megabits per second. Some people don't even get that on their broadband when they're downloading from 10 miles away. And this is from another planet. And at a distance of 400 million kilometers, they still got data rates of 8 megabits per second, which is way, 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 way more than you can possibly hope to get with a radio signal. Some very distant spacecraft, when sending radio signals back to Earth, they're not much better than a few bits per second, or if you're really lucky, a few kilobits per second. Now we're talking about millions of bits per second, orders of magnitude faster, thousands of times faster. So maybe future space missions, if they decide to use lasers rather than radio communication, will be able to send data much faster and perhaps much higher resolution images, much higher resolution video at the same sort of time as it would normally take a radio to send a rather low resolution image. So it looks like that's probably the future of communications. At the moment, it's still a test. They are not going to convert from radio to lasers overnight, but it looks like in the future, this is the way to go. So if you want to learn more, Cassini is now no more. It's crashed into Saturn. Bepi Colombo is on its way to Mercury. New Horizons is on its way out of the solar system. Juno is still looking at Jupiter. And we now have these new missions, JUICE and Europa Clipper, on their way to the icy moons of Jupiter. So if you want to know about past missions or you want to know about what's coming up in the next few years, go visit these web pages. Thank you all very much.